In this section of Chapter 2, we learn about scatter plots, correlations, and regressions. In this section, we'll be introduced to analyzing paired sample data. We will discuss correlation and the role of a scatter plot graph. We'll learn about using linear correlation coefficient, followed by a brief discussion of linear regression. All of these principles will be discussed in more detail later on in Chapter 10. Correlation is used to test relationships between two variables. In other words, it measures how things are related. The study of how variables are correlated is called correlation analysis. Correlations are useful because if you can find out what relationship variables have, you can make predictions about future behavior. Some examples of data that have a high correlation include your caloric intake and your weight, the amount of time you study, and your GPA. Some examples of data that have a low correlation or no correlation at all include your sexual preference and the type of cereal you eat, the cost of a car wash, and how long it takes you to buy a soda inside the station. A linear correlation exists between two variables when there is a correlation and the plotted points of the paired data result in a pattern that can be approximated by a straight line. Scatter plots are similar to line graphs. A line graph uses a line on an XY axis to plot a continuous function, while a scatter plot uses dots to represent individual pieces of data. In statistics, these plots are useful to see if two variables are related to each other. A scatter plot gives you a visual idea of what is happening with your data. The only difference between a line graph and a scatter plot is that a line graph has a continuous line, while a scatter plot has a series of dots. Scatter plots in statistics create the foundation for simple linear regression. A scatter plot, or a scatter diagram, is a plot of paired XY quantitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the first variable x, and the vertical axis is used for the second variable y. In this example, we have a scatter plot of waist and arm circumferences. In this study, each participant had their waist measured and they had their arm measured. Let's let X represent the waist measurement and Y represent the arm measurement. Each red dot in the graph represents the two measurements of one participant. If we study the data in the scatter plot, we see that in general, as waist circumference increases, then arm circumference also tends to increase. This suggests that there is a correlation between waist circumference and arm circumference. In this example, our X values are the weight of individuals and the Y values are the pulse rates of those individuals. In studying the data in this scatter plot, we can see that there appears to be no linear pattern to the data. This would suggest that there is no correlation between the weight of a person and their pulse rate. The linear correlation coefficient is denoted by R, and it measures the strength of the linear association between two variables. The computed value of the linear correlation coefficient R is always between -1 and +1. If R is close to -1 or if it's close to +1, we say there appears to be a linear correlation. If R is close to 0, we say that there does not appear to be a linear correlation. A correlation coefficient of 1 means that for every positive increase in one variable, there is a positive increase of a fixed proportion in the other variable. A correlation coefficient of -1 means that for every positive increase in one variable, there is a negative decrease of a fixed proportion in the other variable. 0 means that for every increase in one variable, there is no positive or negative increase in the other variable. The two just aren't related. Let's consider these data of shoe print lengths and the heights of males. The researchers want to know if there is an association between shoe print lengths and the heights of their male subjects. The researchers measured the shoe print length and the heights of their 5 male subjects and plotted these data in a scatter plot. Looking at the scatter plot, it is not clear if there is a linear correlation. We can calculate a linear correlation by hand using formulas we will learn about later on in Chapter 10, or we can use one of several statistical tools to calculate the linear correlation coefficient R on these data. On a side note, you can refer to page 579, Appendix C of this textbook to find out more information of some statistical apps that are available online. However, you can also use Microsoft Excel to calculate linear correlation coefficients as well as many other statistical calculations. The researchers in this example used the app DACC to calculate the results of a linear correlation coefficient and found that R was equal to 0.591. Because our correlation is positive, we know that there is a positive association between shoe print length and heights of males. But now we want to determine if there's a strong association between our two variables. We can use the p-value to help us to determine if there is a strong linear relationship. If there really is no linear correlation between two variables, the p-value is then the probability of getting a sample data set with a linear correlation coefficient R that is at least as extreme as the one obtained from our sample data set. Going back to our shoe print example, we see that the DACC has provided us a p-value of 0.294. This p-value tells us that there is a 29.4% chance of getting a linear correlation coefficient of R equal to 5.91 when there is no linear relationship between the two variables. Only a small p-value, such as 0.05 or less, suggests that the sample results are not likely to occur by chance when there is no linear correlation. So a small p-value supports a conclusion that there is a linear correlation between our two variables. Now let's look at the same comparison between shoe print lengths and the heights of males. But this time, the researchers took the measurements from 40 subjects. In this scatter plot, there does seem to be a distinct pattern. In other words, as shoe print lengths increase, the heights of the male subjects also tend to increase. This time, the researchers used a statistical application called Minitab. And with the larger sample size, we see that the linear correlation coefficient of R is equal to 0.813, and it has a p-value of 0.000. Because the p-value of 0.000 is so small, we have sufficient evidence to conclude that there is a linear correlation between shoe print size and the heights of males. A regression line is simply a straight line that fits the data. So with a given collection of paired sample data, the regression line is a straight line that best fits the scatter plot of the data. The regression line can be expressed as the formula y hat equals to b naught plus b1 times x, where b1 is the slope of the line and b0 is the intercept of the line. We can use the regression line to make predictions about our y variable based on the value of our x variable. Let's go back to our example of shoe print lengths and the heights of males. If we want to create a regression line that best fits our data, we can use our statistical tools of choice to achieve this. In this example, the researchers again used DACC. From the DACC results on the left, we see that the y-intercept of b0 is equal to 80.93041, or rounded up to 80.9. And the slope of b1 is equal to 3.218561, or rounded up to 3.22. The equation of our regression line for these data would be y hat equals to 80.9 plus 3.22 multiplied by x. In other words, height equals to 80.9 plus 3.22 multiplied by the shoe print length. In order to make a prediction about a male subject's height, we would simply put that subject's shoe print length into the formula, and the result would be our estimate of the height for that male subject. This is the end of Chapter 2. I've posted the homework for Chapter 2 onto Canvas already, and I've extended the deadline for this homework to be Monday, September 7th.